Hi everyone, we're Team V Salad. That's Victoria, Scotty, Adam, Laura, Aaron, and Dylan from Knitline Chemicals. And today we're going to talk to you about our design for a process for the production of styrene. So our presentation is going to focus on several different things. That includes the chemical background, so kind of who we are, why we're doing what we're doing, and the chemical basis for the design. The details of the process, so the nitty-gritty of exactly what is in our design. Our economic analysis, where we determined whether it would be economically feasible to produce styrene in this way, and our recommendations for the future of the project. So, Knitline Chemicals, as we know, is a major olefin producer, and a side product from olefin production is a mixture of C4s. And there isn't much of a market for C4s right now, so it would be clearly beneficial for Knitline Chemicals to be able to turn these undesired side products into something that we can sell. We have determined through our marketing department that styrene could be a possible pathway for these C4s because it can be made from 1,3-butadiene, which is one of the C4s in the mixture. There appears to be a fairly strong market for styrene at the moment, and we have also determined that we could upgrade one of our current plants on the Gulf Coast to be able to accommodate this styrene production. How this would be done is through two main reactions. Styrene can be created from 1,3-butadiene through the dimerization of butadiene into vinyl cyclohexene. This has one major side reaction, which the butadiene also dimerizes to create 1,5-cyclooctadiene. And the second main reaction is the vinyl cyclohexene being oxydehydrogenated while reacting with oxygen into styrene. And this similarly has three main side products, which are benzoic acid, ethylbenzene, and benzaldehyde. So clearly, the goal for this design would be to maximize the conversion of butadiene to vinyl cyclohexene and vinyl cyclohexene to styrene, while minimizing the selectivity of these side products. Our design, just kind of an overview, can produce about 95,000 pounds of styrene per hour, and at an operating time of 8,400 hours per year, and that will give us a yearly production of about 800 million pounds of styrene. And at a price of 65 cents per pound, that gives us about $516 million in yearly revenue. So clearly, styrene has the potential to be a profitable venture for Knitline Chemicals. So we will now go through our design in more detail.
Thank you, Laura. My name is Aaron, and I'm going to be talking about the generic schematic for our plant. All those side products that are made in those two reactions have to be dealt with, and the main way we deal with them in our plant is through distillation. So, our first extractive distillation column is actually being outsourced from another company to deal with all the feed in the seed 4 that we do not want. This is basically everything except for 1,3-butadiene. The 1,3-butadiene is then sent into reactor 1, where it is turned into the vinyl cyclohexene. The vinyl cyclohexene is then sent into one distillation column where we don't get the greatest separation, so we send it into another. And this pulls off all of the excess 1,3-butadiene, which we later burn for fuel. The vinyl cyclohexene recombines with the initial stream and is sent through another distillation column to get rid of the side products from that first reactor. Now that we have a pure vinyl cyclohexene stream, we send it into a mixer. This mixer has been designed to deal with any trace amounts of 1,3-butadiene that could possibly combust with the oxygen. Once everything is safely mixed, along with some steam, we send it into the second reactor. This second reactor makes our one product styrene, but this styrene comes with all those side products we mentioned before. Our first distillation column pulls off the benzoic acid and not all, but most of the water. Another distillation column gets us pure water we use for a recycle. This distillation column down here gets us almost pure water, but it has a small amount of organics, so we have to send it to wastewater treatment. The other stream is almost 50-50 water benzoic acid, so it has to be liquid incinerated. The top stream is sent to a three-phase separator. This three-phase separator pulls off more of the water, leaving us with styrene, vinyl cyclohexene, ethylbenzene, and benzaldehyde. This is then sent to another distillation column where that benzaldehyde is removed. Now that we have the benzaldehyde out, the only side product we have left to deal with is the ethylbenzene and the excess vinyl cyclohexene. The vinyl cyclohexane is removed here and sent back to the reactor and recycle. There's also a purge stream here to deal with in order to keep our concentrations of side products low in the reactor. The stream that continues out here is the ethylbenzene and the styrene. The ethylbenzene is extremely difficult to get out from the styrene, so we had to use a system similar to extractive distillation. This took cyclohexane, and sends it through the distillation column with it. This cyclohexane allows the ethylbenzene to be pulled off the top and the styrene to come out as a pure product with over a 99.9% purity and able to be sold.
Hi, my name is Victoria and I'll be talking about how well our process meets specifications as well as some inherent issues such as environmental concerns with our process. First of all, our process meets all hard specifications such as safety concerns and other specifications. However, we do not meet a soft spec of overall vinyl cyclohexene recovered as styrene product. We hoped to attain a recovery of 98%, however, we were not able to design a process that got us past 94% recovery. However, since this is a soft spec, we felt that it was reasonable and that our process was valid as designed. Some of the hard specifications that our process does meet are products from our first reactor all correspond to the pilot plant data, and therefore our kinetic parameters seem to be accurate. Our input to our second reactor had the correct proportion of oxygen to VCHX, which is quite important for the reaction to run as expected. Also, our concentration of 1,3-butadiene was below 50 ppm, meaning that our second reactor would not explode, as 1,3-butadiene is quite combustible in the presence of oxygen. The products coming out of our second reactor are also within the pilot plant data, and therefore our kinetics function as expected, and our styrene purity was over 98.8%, or 99.8%, sorry, at 99.9%, so that is a sellable product. The process has several issues inherent to the design and the chemistry of the main components. First of all, most of the separations that we have to deal with are quite difficult, and therefore our process was designed at vacuum conditions. This led to increased costs associated with our distillation columns, as well as a slight increased risk of implosion. However, because of the way we designed it, this risk should be mitigated. Additionally, benzoic acid is present in our process, as well as some other acidic components, which would lead to increased corrosion of our equipment. And lastly, styrene monomer polymerizes at high temperatures, so we had to limit the temperatures of our final separations, as well as put refrigeration in place for our product. This process has several environmental concerns, such as our CO2 emissions, which are at about 23 million pounds per year. Moreover, benzoic acid is toxic to aquatic life, so we had to send our benzoic acid waste stream to a liquid incinerator. If we were able to purify this further, we could perhaps sell it or sell it as a molar solution. However, this option was not deemed feasible. Moreover, several components of our mixture, our input mixture, are highly combustible, such as 1,3-butadiene and basically all of their C4s. Vinyl cyclohexene is carcinogenic, and styrene is also carcinogenic and toxic. Therefore, many safety measures had to be put in place to ensure that we would not have a chemical spill. Next, you will hear from Dylan regarding economic analysis.
Thank you, Victoria. I'm Dylan, and I'm going to handle the first part of the economic analysis and hand it over to Adam to finish. So, our styrene plant costs $446.6 million capital costs, and it comes mostly from our IBO and OBO costs. So for our IBO, our main cost comes from our C4 extractive distillation columns, our reactor designs, our distillation columns because they're all running under vacuum pressure to make the separations easier, and our heat exchangers along with the engineering costs. Our major OBO costs come from our storage of all of our chemicals off-site, along with the boiler upgrade and the cooling water upgrade. Our operating costs throughout the year is about $260 million, and the major cost comes from our butadiene extraction. This cost is associated with the operating costs of the butadiene extraction column, along with the licensing fee that we have to pay. The second biggest cost is our hot oil. The hot oil is used in our reactor cooling, along with some distillation column, condenser cooling, and some heat exchanger heating. And then our third main cost comes from our low pressure steam, which is used throughout the process to be cost effective compared to using high pressure or medium pressure steam. Now I'm going to hand it over to Adam.
So thank you, Dylan, for covering the cost aspect of the economic analysis. My name is Adam, and I'm going to talk about the cash flow aspect of the economic analysis. Is it profitable for us to continue with the project and with the current process and design? Now, it is good to note that there's a slight but insignificant error on the submitted files, and it has since been fixed and presented in this presentation. So with the current market price for styrene and netback of 65 cents per pound, we found that the rate of return can't be calculated because it's way less than negative 30%. And with that netback price, our net worth sums up to be a negative $661 million, which means we will be operating at a loss. Now, if we were to increase that netback up to 30% with the price of 88 cents per pound of styrene, the rate of return, the IRR, would be 0%. And that would give us a break-even netback at 88 cents per pound. But still, the net worth would be negative $75 million. So even if the netback was increased by 30%, we will still be operating at a loss. Now, if the price of styrene was increased by 50% at a netback of 95.8 cents per pound, we'll reach our goal of rate of return of 20% and a netback of $122 million. But this is assuming that the market price for styrene increased by 50%. But still, at this current market price, it's not profitable for us to continue with the design.
Thank you, Dylan. Thank you, Adam, for the economic analysis. My name is Scotty, and I'm here to present our group's final conclusions and recommendations. So, while it is true the plant can produce $544 million a year worth of styrene, the costs associated with this process grossly exceed this revenue. For example, we decided it was necessary to purchase a butadiene extraction system from an outside company, and the costs associated from running this between the operating expenses and licensing fees total in at 8.91 cents per pound styrene produced. This is necessary, however, as extracting butadiene from a mixed stream of C4s is incredibly difficult and would require multiple distillation units. Also, throughout our process, there are numerous heat exchangers, several of which require very intensive heating and cooling, which the best way to achieve this is by using dialtherm oil, and this cost totals in at 8.61 cents per pound styrene produced. Lastly, there are some waste disposal fees. There's benzoic acid produced throughout our process that, while it could be sold as a product, in order to separate it, it would grossly exceed the extra costs we would gain from selling it. And so, in order to dispose of this, it has to be sent to a liquid incinerator, as benzoic acid is very corrosive and cannot just be disposed of with wastewater. And this cost totals in at 3.33 cents per pound styrene produced. And once we factor in the costs of maintenance, raw materials, all these costs grossly exceed that $544 million a year. And so we recommend that the company does not yet pursue creating the styrene plant. The company would be losing money, which makes it uneconomical to be built, and we don't believe this idea should be entirely scrapped. And while we wait for changes in the market, the plant could be better optimized, or if there are changes in the market, for example, if the price of styrene goes up to 88 cents per pound, then we would be breaking even. Or if we wanted to hit that 20% ATROR, then the cost would have to go up to 98 cents per pound. And so, in conclusion, this chemical plant would not currently make a profit for the company. The high utility and raw material costs grossly exceed the revenue generated, and that sums up our project. We're Team V-Solid, and we wanted to thank you for your time today.